Today's class will be a short one. We'll discuss about the applications of plane stress in pressure vessels and cylindrical vessels, spherical pressure vessels and cylindrical vessels. So first thing we'll look into the stresses which are acting on a spherical thin-walled vessel. We'll discuss about the membrane stresses, and then we'll calculate stresses acting on the outer surface of the pressure vessel and the inner surface of the pressure vessel. We'll also determine the maximum shear stresses. Then we'll go to the cylindrical pressure vessels. There will be two types of stresses. One is the longitudinal stress and the other one is circumferential stress or the hoop stress. So we will determine those expressions, determine the longitudinal stress and hoop stress, and then again we'll calculate the shear stress. We'll calculate the stresses on the outer surface and the stresses on the inner surface. Also we'll calculate the shear stress, maximum shear stress. So these are some shell structures which are this is in Delhi, this one, and some more structures you can see. And this shell structure is a submarine. So it consists of two hulls. One is the interior one and the other one is the exterior one. So these hulls will house the submarine. Like it gives the space for the placing equipment and all the machines in the submarine. So the design involves understanding what are the stresses which are acting on these shells due to the pressure. So there will be pressure both from the water outside and there will be some interior pressure which so both will balance out, and there will be stresses acting on these hulls. So you can find out what is the maximum stress and then do the design. So this is a shell structure of a aircraft cabin. So when you fly a airplane, the atmospheric pressure is very low, and you have to create pressure inside the cabin so that the structure will not collapse. And so again there will be some internal pressure will be there on the shell. And the spacecraft also there will be internal pressure to maintain the shape of that the outer atmosphere. So pressure vessels are closed structures. They can contain liquids or gases under pressure. So tanks, pipes, pressure cabins in aircraft and space vehicles are some examples which are seen. So when pressure vessels have walls which are thin in comparison to their overall dimensions, they are known as shell structures. So submarine hulls and two more examples are there: roof domes and airplane wings. Those come under shell structures. So we'll discuss about spherical pressure vessels. So here we have a circular spherical pressure vessel. The radius, we have the diameter, and there will be thickness of this vessel. So the thickness is very small compared to the radius or the diameter. So here to be classified as a thin walled pressure vessel, the radius to the thickness ratio means that radius should be at least 10 times greater than the thickness. So here what you are assuming is the internal pressure is exceeding the external pressure. So the net pressure will be outward. So the net pressure P is shown here. It is called the gauge pressure, and it is the difference between the internal pressure minus the external pressure. And if you cut a cross section along, so we cannot make a circular vessel directly. We have to assemble them. We have to so this is upper part and this is the lower part, and we are welding it along this circumference. So if you consider if you cut the section there and see what are the stresses acting, so we can calculate that, and that stress will be balanced by, means whatever pressure is coming on this entire dome, will be balanced by the reactions which are or the stresses developed along the circumference. So we can do that analysis here. So the net upward pressure along that weld is P times pi r square. Pi r square is the projection of that circular dome. So we'll do that analysis. So first thing we'll do, we have this circular cross section. We cut a plane passing through the diameter. So this will be, so we can look at the left part of the structure and see what are the forces. So there will be the internal pressure forces due to P, capital P, that is small p times pi r square, and there will be stresses developed on the circumference, a thin circular area along the circumference. So there will be the stress sigma. So this stress sigma times that circular annular area will balance out this pressure. So we can write that equation. We assume that there is no variation of the sigma along the thickness. Because the thickness is very small, we can approximately assume that it is uniform. So sigma will be the total force in the rightward direction will be circumference is 2 pi rm times t. What is rm? Rm is the mean radius. So there will be inner diameter. So this circle will have, there are two circles actually. There is interior circle and the outer circle. So the average of those two radius is the rm. So we can write rm as r plus t by 2, and this will be balanced by the p acting in the leftward direction. So sigma into 2 pi rmt minus p pi r square. This net equilibrium is force equilibrium in that horizontal direction is 0. So we'll get stress sigma as p pi r square pr square by 2 rmt. So pi and pi will cancel out, and we are left with pr square by 2 rmt. So what we can do, we can write rm by r by sending this one of the r to the denominator. So what will happen is we'll have pr by 2t, and we'll have in the denominator we are sending rm by r, so it will be 1 plus t by 2r. So that is what is coming here. So this is the exact expression, and if thickness is very small compared to the radius, that is the interior radii, then this term can be neglected, and we'll have stress is equal to pr by 2t. So yeah, stress is directly proportional to the internal pressure, and it is also proportional to directly proportional to the radius. So larger is the pressure vessel, more is the stress coming onto it, and it is inversely proportional to the thickness. So if the thickness is increased, then stress will reduce, and yeah, that's it. Or if thickness is reduced, the stress will increase. So this is the expression for stress sigma on that circular annular area. Now what we can do, we can, yeah, on the pressure vessel, because of symmetry, the stress on the surface will be equal in both the directions. So sigma, whatever stress is there, the same sigma will act on the other direction also. So that we are doing that approximation by neglecting r by 2t term, and we will have sigma is pr by 2t. So this stress is a uniform tensile stress. It acts along the tangent. For that small area, if you see, it will be acting along the tangent, and these are called the membrane stresses. And what is the, so these are some bubbles. So let's calculate the stresses on the outer surface. So on the outer surface, what is happening? Our outer surface, there is no. Let's think that this is sigma x and this is sigma y. So in the out of plane direction, that is in the z direction, there are no stresses. So sigma z is 0. Also tau x z or tau x or tau zx and tau zy also are 0. So you can imagine this to be like a principal. These are the principal planes. Sigma and sigma are the principal planes. Sorry, sigma and sigma are the principal stresses, and these lines are the principal planes. So on the outer surface, we are looking at the stresses and see what is happening there. So on the outer surface, what is happening? We have the only the in-plane stresses, sigma in the x direction and sigma in the y direction. Outer plane, there is no stress. So for this, what is a Mohr circle? What is a Mohr circle for this in-plane stresses? Can anyone answer that? Can raise your hand if you want to answer. Like you can raise your hand and try to. What is the Mohs circle for this one? Any answers from anyone? Are you able to hear me? So, excuse, you are able to hear, right? So,
Yes,
yeah, you can
sir.
tell me what is the Mohs circle for this plane stress scenario?
Shear stresses are acting, sir. I think we cannot draw more circle.
Yeah, okay, you are on point. So, what is happening here on the left face and the top face, or right face and the top face? We have sigma comma 0, and on the this right face is sigma comma 0, and top face is also sigma comma 0. So a and b, whatever m and n points are on the sigma theta tau theta axis are on the coinciding. Okay, so we cannot draw a Mohr circle there. Okay, so that is what we have for this specific for this case. We don't have Mohr circle. We just have a single point for the in-plane stresses. But we can draw the Mohr circle for the out of plane, considering sigma z and sigma x, or sigma z and sigma y. Okay, so that Mohr circle will result in some shear stress. And what will be the shear stress there? Maximum shear stress. What will be the maximum shear stress? Maximum shear stress will be out of plane now. So what will be the maximum shear stress? So if you draw the Mohs circle for say sigma y and z direction, so y and z direction, so it will be sigma comma 0, and on the z it will be 0 comma 0. So a circle, if you draw, will have a diameter of sigma. So the tau max will be sigma by 2. So it will be PR by 4t. Okay, so and on the inner surface, so if you're drawing the Mohs circle for the interior surface, there will be sigma and sigma acting on the in the x and y, and there will be this compressive stress because there is a pressure acting there. There will be a compressive stress P. Actually, sigma g direction is shown like this, so this minus sign should be removed, I think. Yeah. So anyway, there is a compressive stress acting there. So in this case, again, the Mohr circle in the x and y axis there will be no Mohr circle. There will be just a single point. But you can draw Mohr circle for the out of plane stresses. So out of plane, if you consider y and z, so the say you can say B will be sigma comma 0 and C will be minus P comma 0. So you can draw a circle, and the maximum shear stress will be sigma plus P by 2, which is PR by 2T plus P by 2. So yeah, so for this case, outer surface, this is the stress values, and the normal stress in the z direction is 0. So the maximum shear stress will be for the Mohs circle with y and z axis, or x and z axis. So that value is PR by 4T. The in-plane shear stress is 0. If you see, there is no in-plane shear stress because all the forces are in tensile direction. Okay, so any if you consider any plane, there are no shear stress. Okay, for this specific case, there will be no shear stress. Okay. So if you cut a plane in the other if you rotate in any way, there are no shear stresses. Okay, so that is what we have in this one. And for this case, we have sigma 1 and sigma 2 PR by 2T, and sigma 3 is minus P. So for rotation in this XY plane, there are no shear stress. So this shear stress and this shear stress are 0. Tau xy and tau yx is 0. But in the out of plane, that is tau xg, so tau zx. So tau zx will be in this direction on the front face, and tau zy will be in the upward direction on the front face. So those will have some values, and the maximum shear stress in xg or gx or zy will be absolute value of sigma 1 plus absolute value by 2. So it will be PR by 4T plus P by 2. Okay, so that is what we have here. Similarly, we can analyze for cylindrical pressure vessels. So some of the real life cylindrical pressure vessels you can see here. One is the gas cylinder which you use in your kitchen. So inside there will be some gas, and it will have some, it will be exerting pressure on the walls of this cylinder. Similarly, there are some pressure vessels which store some liquids, or again it can store some gas. So again they will exert external pressure on this cylindrical wall, and also on this spherical, probably it's not exactly spherical but some curvy dome. Okay, so we can do the analysis for this thing, for this cylindrical pressure vessel. So there will be two stresses acting. One will be in the longitudinal direction. Okay, so the one stress will try to expand the cylinder in this direction along x in the horizontal direction, and there will be another stress which will be acting such that it will try to increase the circumference of the circumferential area of the cylinder. So that stress is called the hoop stress. Why it is called hoop stress? We can discuss that now. So these are some examples of the pressure vessels, and so first stress is we'll discuss about the circumferential stress, which is the hoop stress. So the circumferential stress or the hoop stress is this one, sigma 1. Okay, it is acting in the along the tangent, and it acts along that circular area. And sigma 2 is the axial stress. It is also called the longitudinal stress. It acts along the length of the cylinder. So why is it called hoop stress? I think you might have seen some barrels, and those barrels are barrels holding some liquid made of wood, and those are there are wooden planks. And what you do is you put a steel hoop around that wooden tank, wooden barrels, so that the strength of the capacity of withstanding the pressure, liquid pressure, is increased. Okay, so those are the circular hoops which are placed around those wooden barrels. So from that terminology, they are using this sigma 1. They are calling the sigma 1 stress as hoop stress. So how to find this circumferential stress or the hoop stress? So what we'll do, we can again do similar analysis. We'll cut a cross section along the diameter along the length. Okay, and then we'll do the free body diagram. So we have cut a cross section along the length, and once we have cut the cross section along on that annular area, we have that this small rectangular area. We have the stress sigma 1, which is the circumferential stress or the hoop stress, and the pressure of the liquid or the gas is acting in the along this direction, and that value of the pressure is P times the area of the projected surface. Okay, so this circle, this semicircle will project as a rectangle here. So the area of the rectangle will be B times the diameter. So we have P times B times 2R, and on this the stress due to the force due to the stress, we can calculate as sigma 1 times thickness times B. Okay, so we have sigma 1 times thickness times thickness both from the top and from the bottom, so it will be 2T, and that will be balanced by this 2PBR. So from this we can get sigma 1 value. So what we can do, we can cancel out 2B, and we'll get PR by 2T, PR by T. So this is the hoop stress. So sigma 1 is PR by T. Now we can calculate the axial stress. Again, to calculate the axial stress, we'll cut a cross section perpendicular to the length, and once you cut it, we can draw the free body diagram. So this is the stresses on that circular annular area, and this pressure is acting. Both are balanced, so we can calculate, we can do the force balance and find the sigma 2. So the force along the length due to the stress sigma 2 will be sigma 2 times 2 pi r times T, and and this force will be P times the circular area, which is pi r square. So from this we can get the axial stress. So what we will do, we will cancel out pi and send the 2 down, and also r also we can cancel out, and we will get PR by 2T. Okay, so this is the axial stress in that cylindrical pressure vessel. So we see that the hoop stress is higher than the longitudinal stress. Okay, so stress on the circumference, it is more. It is twice the axial stress. So now we again will look at the, what we'll do is we will draw the Mohr circle for the, look at the stresses on the inner surface and the outer surface. So on the outer surface, again we have sigma x, sigma y, and sigma z is 0. So we will have no Mohr circle for in-plane stresses. So sigma 2 comma 0, sigma 1 comma 0. So sigma 1 is higher than sigma 2. So this quantity will be the capital A, and sigma 2 will be the capital B. So we can draw a Mohr circle, and for that Mohr circle we can find the shear stress. So the maximum shear stress will be, in-plane shear stress will be sigma 1 minus sigma 2 by 2. And we can also have Mohr circle for stresses in y and z direction. So for that, this point will be sigma 1 comma 0, and the other point will be 0 comma 0 for along the z axis. So in the further direction, the Mohr circle maximum shear stress will be sigma 1 by 2. And if you draw Mohr circle for along z x and z axis due to rotation about y, the maximum shear stress will be sigma 2 by 2. Okay, so yeah, sigma 1 is PR by T, sigma 2 is PR by 2T, sigma 3 is 0, tau max for xg plane. So you are looking at the xg plane and rotating about y. So that will be sigma 1 minus sigma 3 by 2, sigma 3 is 0, so it will be PR by 2T. Sigma 1 is PR, oh sorry, sigma 1 is what? Sigma 1 is PR by, something wrong here. No, okay, sigma 1 is PR by T, so it will be PR by 2T. Similarly, tau max yg will be sigma 2 minus sigma 3 by 2, which is PR by 4T. But I think there is some mistake here. What is the mistake?
Sir, T max xz is equals to sigma 2 minus sigma 3 by 2.
Yeah. Sigma 2 minus sigma 3. Yeah, because we are looking. Oh, no. I think it's okay. Because, see, sigma, we are looking at the xg plane, right? Yeah, xg, we are looking at the xg, so it will be sigma 2 minus, yeah. So what we have to do, we have to change the things. This error here, so I'll correct it. This I can't correct it now. So yeah. So there is a small correction. Okay, this should be sigma yz. Okay, and this should be sigma xg. I think then it will be okay. And then for the in-plane stress will be sigma 2 minus sigma 1 minus sigma 2 by 2. So this is okay. Tau max xy is sigma 1 minus sigma 2 by 2, which is PR by 4T. I think for the first case it should be sigma yz. It should be yz. Okay. Only then we can have this sigma 1 minus sigma 3 by 2, and second case it will be sigma xg. So in that case we'll have sigma 2 minus sigma 3. Yeah. So here the maximum shear stresses are again PR by 2T, and it is acting in the out of plane direction. Okay, it is acting in this, maybe it is acting along this plane. Okay, I'm just showing it by this arrow or by this cursor. So it will be this plane, the diagonal plane, vertical diagonal plane. Okay, and the other vertical diagonal plane also will have the maximum shear stress. And remaining two planes, like one which is this diagonal, this inclined diagonal, that will have PR by 4T. And for the inner surface, again we have the compressive pressure acting on the yx plane. So we can find the maximum shear stresses. So it will be for this xy plane, it will be sigma 1 minus sigma 2 by 2, which will be same as this value, which is PR by 4T. And for the remaining two cases, I think again I have made the same error here. It should be yz and this should be xg. So yz will be sigma 1 minus sigma 3 by 2. So pr by 2t plus p by 2, and xg will be pr by 4t plus p by 2. Okay, so these are the shear stresses. And where will be the maximum shear stress? I think pr by 2t plus p by 2. Again, we are having the maximum shear stress in this vertical diagonal plane. Okay, this plane we are having the maximum shear stress. I think today's class will end now, because although I made some slides on, I have prepared for some bending and all, but I will do that maybe on I will start that from Monday. Probably today's class will end here.